Hi, this is Brandon Baines in the Math Department at Lipscomb University, here to talk with you about compound interest and exponential growth. In this presentation, you'll learn how to compute compound interest using exponential functions, and you'll learn how to calculate growth and decay using exponential functions. Compound interest is interest computed on the original investment as well as the interest that has accumulated over time. So this compound interest really is interest on top of interest. Compound interest is generally computed every certain interval of time. So some common intervals are yearly. So in that case, the interest would be computed once a year. Monthly, the interest would be computed once a month. Semi-annually, it's twice a year, or quarterly, 4 times a year. We also have a classification of continuously compounded interest. This really is considering that the interest will be computed at every possible moment of time. So the number of computations goes to infinity. It may be helpful for us, since we usually deal with minutes and seconds, to think about this as being computed every second. We have 2 compound interest formulas depending on how the interest is computed. The first is for interest that is compounded a finite number of times per year. So we generally say n times per year. The second one is when the interest is compounded continuously. Okay, that is, again, at every moment in time, and we have a different formula for that. So let's look at the first one. The amount A in an account T years after an initial investment, that's P dollars, deposited into an account with interest that's compounded N times per year at a rate, always as a decimal, called R, is given by the equation A equals P multiplied by 1 plus R over N raised to the N times T. You'll see here that this actually forms an exponential function. We could call this A of T, the amount at any given time T. The second function or second equation for continuously compounded interest is A equals P e to the RT. So E in this case is the number E, that's approximately 2.7. You'll also note that this is an exponential function. We could also call this A of T equals P e to the RT. That would give us the function for the amount in the account for any given value of time. Let's look at an example. A young man wishes to invest $5,000 into a savings account. At the bank, he is presented with the following options. Option A, interest is compounded quarterly at an interest rate of 3%. B, interest is compounded monthly at an interest rate of 3%. And option C, interest is compounded continuously at an interest rate of 3%. The young man plans to leave this money in the account for 20 years. He wants to know what option will give him the most interest. Option A, we would have the following. A equals 5,000 multiplied by 1 plus 0.03. Notice that that's the interest rate as a decimal, divided by 4. 4, because that's the number of times the interest is compounded per year, raised to the 4 times 20. 20 for 20 years. And again, 4 is still the number of times it's compounded per year. It results in $9,090.22. Option B, using the same formula, but with a different number of compounds per year of 12, results in $9,103.77. If we compare option A and option B, we see that option B yields more money in the account after 20 years than option A. Option C, continuously compounded interest. Again, we're using A equals PE to the RT. So that's 5,000 times E raised to the interest rate as a decimal multiplied by the number of years. So that's multiplied by 20 years. This gives us $9,110.59. And that's higher than options A or B. So the young man should choose option C if he wants the most money. Another scenario that we can model using exponential functions is exponential growth and decay. Some common examples of populations that are modeled with this exponential growth decay model are things like bacterial growth, the amount of drugs in blood over time, the national growth, and half-lives. The exponential growth decay model is actually nothing new. It's the same equation as the continuously compounded interest that we just discussed. So we're going to use A equals PE to the RT to represent the amount of a certain substance, T years, after T years of growth, growing at a certain rate as a decimal, and having some initial population that we'll call P. This is all the same setup. In this case, since things could be growing or decaying, we do have the option of our rate being negative, and that would represent exponential decay if the rate is less than 0. If the rate's positive, then we're representing exponential growth. Let's look at an example. Researchers are studying a new strain of a certain bacteria by observing the growth of the bacteria in a petri dish. They begin with 100 bacteria in the petri dish and measure the amount of bacteria each day. The researchers modeled the growth of the bacteria with the function A equals 100 multiplied by e to the 0.3t, where A is the amount of bacteria t days after the bacteria is placed in the petri dish. We may be interested in knowing how many bacteria will be in the petri dish after 7 days, or how many bacteria will be in the petri dish after 100 days. Using the exponential growth model, we have in part A, the amount of bacteria is 100 multiplied by e to the 0.3 times 7, which results in 817 bacteria. In part B, we have A equals 100 e to the 0.3 times 100, which results in 1 quadrillion bacteria. I had to look up the name of that big number there. That's a quadrillion. I rounded all the answers in that scenario to the nearest whole number.